OK, I guess that everyone managed to grab a cup of coffee by now, so I think we can get started. Yeah, I'll start by the introductions. So my name is Marc Nuri. I work as a software developer for Red Hat. I'm currently working on 2 free open source projects, the Fabricate Kubernetes client, which we'll briefly see today, and Eclipse JQ. I'm also the author of the book Full Stack Quarkus and React. This book is somehow related with what we are going to see today. It digs deep in some of the topics that we'll see. So if you're interested on the talk and you want to learn more, please feel free to check it out. I'm available on almost every social network, on LinkedIn, on Twitter, Mastodon. I'm on Gitter, on GitHub. So if you have any questions regarding the project, the book, or the talk, or anything that you think that I can help out with, please feel free to reach out. I will be really glad to try and answer any questions you may have. OK, so yeah, the purpose of today's talk is to answer the question of how can we consume events reactively right from the source until the user, all through the stack, right? And for this purpose, I'm going to use a project I developed a few years ago, the Yet Another Kubernetes dashboard. So yeah, I will start the talk explaining a little bit what is a reactive application. Then I will continue explaining why I chose Kubernetes as a way to illustrate the advantages of this approach when tackling the development of applications. Then I will go a little bit over the implementation that's been followed in the Yet Another Kubernetes dashboard, both the backend and the frontend, very briefly. And finally, I will show in a live demo the advantages of reactive applications, and then in a final slide, what are the trade-offs and challenges and how we can mitigate them. Yeah, so reactive is a really overloaded term. So the first thing I want to do is to say what I understand with reactive. And for this purpose, I think that the best source is the reactive manifesto. The reactive manifesto really talks about systems, but I think that we can extrapolate those definitions into reactive applications too. I really like the reactive manifesto because it centers, or the cornerstone is usability, responsiveness. It centers everything on the user. It says that for a software application or for a system to add value, it must be usable. It must remain responsive at all times. It must respond in a timely fashion, even if parts of the system are broken or there are problems. Problems should be detected early, and they should be dealt with. Probably the system should be able to self-heal or self-reparate itself. And in order to create this responsive software, we need to design it to be both resilient and elastic. What do I mean with resiliency, or what does the reactive manifesto mean with resiliency? It means that you need to embrace failure. You need to consider failure as a first-class citizen. Most of us here are developers. We know that errors and problems are bound to happen. So we should take those into account when we are actually designing the system. We should design the systems to be able to self-heal themselves. We should make several components. These components should be isolated one from each other. And whenever one of these components fails, it shouldn't affect the rest of the system. So the system should remain at least somehow usable. We should also design our systems to be elastic. This means that the system or application should be usable regardless of the workload. My system should have the same behavior if it has 1 user or 100,000 users. This means that this system needs to be able to scale up, right? It needs to be able to provide multiple replicas of itself, but also scale down. Whenever the workload lowers, we need to be able to optimize the resources and make the system more economic. And how does the reactive manifesto tells us to achieve this resiliency and elasticity? It tells us that we need to make our systems message-driven, or our applications message-driven. So we are starting to talk about this asynchronous, non-blocking communication between components, right? We define these components that have clear boundaries, that they are isolated, and in this way, we can achieve this resiliency that we were talking before. We will also be able to scale these components independently, so we will achieve this elasticity too. Yeah, this is a really complex topic. We could spend many hours talking about this. So if you are interested in this, I recommend the book by my colleague Clement Escoffier and my ex-colleague Ken Finnegan, Reactive Systems in Java. This is a really, it provides a really good overview of reactive systems and reactive applications, and especially is intended for Java developers. OK, so yeah, I thought that we were going to consume Kubernetes events reactively, right? When people present reactive applications, they usually use Apache Kafka or any other kind of message broker as this event source in order to illustrate what are the advantages. However, I thought that Kubernetes is also a good source of events and a good way to illustrate what problems we're trying to resolve and what are the advantages of these reactive systems. So Kubernetes made its 10th year anniversary like 2 weeks ago or something like that. I'm pretty sure that most of you know what it is, but just in case, as the Kubernetes.io website defines it, Kubernetes is a portable, extensible, open-source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. OK, so this is a pretty verbose definition, but basically what it means, simplifying it very much, Kubernetes is a platform to deploy and orchestrate containerized applications. Note that I highlighted 2 words here, containerized and declarative. So containerized, this is important to know. Whenever you want to deploy something to Kubernetes, you need to distribute your application as a container image. This is the way Kubernetes handles deployments. This is important. And the other word I highlighted is that Kubernetes is a declarative system. In Kubernetes, the user declares what he or she wants, and then Kubernetes, the system, will provide or try to provide what it was requested. This is important for what we are going to see next. OK, this is a diagram of the Kubernetes components. This is really complex. I'm not going to bore you with the details because it's not the purpose of this talk. But I want to highlight a few things, right? So you can see that Kubernetes has multiple components. The components have clear boundaries. They have some sort of asynchronous communication. They have replication. So if you can see, Kubernetes shares some of these traits that we use to define reactive systems. OK? This is a nice example. I also wanted to highlight from this diagram the API component. So this Kubernetes API component is the main interface that we are going to use when we are interacting with Kubernetes. Whenever you use kubectl or any kind of Kubernetes client, you are actually talking with this, performing HTTP requests to this kube API component. OK, so I said before that Kubernetes was a declarative system. And what Kubernetes users, in order to be able to configure it or manage the applications that you want to deploy there, are these Kubernetes resources. There are, I don't know, tens or hundreds of resources in Kubernetes, and you can even create your own by using custom resource definitions. But for the purpose of today's talk, I'm going to define 2 of them. So in Kubernetes, a pod is the minimum deployment unit. So whenever you want to deploy an application to Kubernetes, you will be actually using a pod. A pod is 1 or more containers, basically, that share the same network namespace and IP. So when you want to deploy an application in Kubernetes, you probably will define this pod, where you define the container image, maybe the resource limits for your application, volume mounts, and so on. However, if you are actually going to deploy something into Kubernetes, you will probably don't use a pod, but some sort of higher order component. For example, a deployment. This is the other Kubernetes resource that we are going to see. A deployment, what it does, it manages a set of pods. So basically, it handles this high availability that we saw before. It allows you to replicate your application. In a deployment, you will define some sort of pod template, and then the deployment controller will be in charge of issuing or scheduling multiple replicas of your pod. It will also allow you to roll out, update, and roll back your application by changing, for example, the container image name. OK, and yeah, I said that I chose Kubernetes as a source of events, right, as opposed to Apache Kafka or any other message broker, because most of the management of the Kubernetes resources, like we saw before, deployments and pods, follow what we call the controller pattern. The controller pattern, the user states this desired state. OK, I want 1 replica, and then Kubernetes makes sure to provide them, the actual state. Usually, when this is explained, we use this analogy with a thermostat, right? In a thermostat, the user sets the temperature that you want at home. In this example, for example, it's 22.5 degrees Celsius. I want to have this temperature. So the controller, the system, checks this desired state. It observes the room temperature. It sees that the current temperature is 21 degrees. It analyzes the difference. And it says, OK, I need to turn on the heater in order to bring this temperature up. So it will keep iterating. It will compare the actual state with the desired state until a point reaches that, for example, the temperature is the desired temperature, 22.5 degrees Celsius. At that point, the controller will stop the heater. And it will continue iterating. Then the heat will go down, and so on. So in Kubernetes, we have this behavior for almost any kind of resource. And you can see this in the resource definitions. Most of them will have two fields. The spec field, which is where the user will define what he or she wants. So for example, for this deployment, the user wants one replica. Then the deployment controller will take care of analyzing, OK, the user wants one replica. I should schedule one pod. The pod is there, but it's not ready. OK, I will keep iterating until the number of ready replicas matches the one that the user specified. So it's mostly the same that we saw for the thermostat. OK, so in order to be able to observe, for each of these iterations in the controller loop, Kubernetes will keep emitting events, right? So there's a new replica, the replica's ready, etc. And in order to be able to observe these events, we need to interact with this Kubernetes API component that we saw earlier. The problem is that we need to observe each resource independently. We cannot connect to someplace which will update us with everything. So if we want to observe the changes in the pods, we will need to open a connection to pods, kubectl, get pods, watch. If we want to observe the deployments, we will need to do that for that resource. And likewise for any resource that we want to observe. So if we check the previous example and we observe these resources, we might start with a deployment where there are no replicas. So the user said, I want 0 replicas. At this point, the system will keep iterating, but nothing will happen. At some point, the user might say, OK, I want this deployment to have 1 replica. So immediately, we will receive 2 events. One for the pods, OK, I'm going to start a pod, and one for the deployment, where it says, OK, the pod has started, but it's not ready. Eventually, the pod will start creating the containers. So we will get another event. The pod is running, but it's not ready. Another event in both sides. Finally, the pod is ready, and everything is running as expected. The spec matches the status. So yeah, finally, we will get this match state. What we see is that for each iteration, we are going to get these events. And we wanted to design these responsive applications where the user gets this immediate feedback from the system, right? So this is the problem that we are going to try to tackle. And for this, and to show this, I'm going to use this project. This is a project, the Yet Another Kubernetes dashboard. We will go into see how we are going to implement this observation right from the backend until the frontend. So this is a side project, a Kubernetes dashboard. It's a free open source project I implemented a few years ago. It began as a quick start example for one of my side projects. But it really grew out of hand eventually. And yeah, you can see that this began as a quick start because it has an utter lack of tests. So please don't judge me if you check the source code. But anyway, it has most of the features that any other Kubernetes dashboard you find around will have. However, it has a distinctive feature, which is this reactive search that we will see later. Regarding its architecture, this Yet Another Kubernetes dashboard is it consists of 2 components. A front-end side, which is built with JavaScript. It's a single-page application built with React, and it uses Redux as the data storage. So yeah, most of you are Java developers probably, so not very interested. We will go really light over this. The backend side is a Java application. It's built with Quarkus. It uses Vertex and Mutiny as the reactive APIs. And then it uses the Fabricate Kubernetes client to interact with Kubernetes. The Fabricate Kubernetes client also uses Vertex as the HTTP client under the hood. OK, so I keep saying this word reactive, but maybe you are still don't getting what the problem is. And I think that the best thing is to see what the problem is with real examples, okay? So this is the Kubernetes dashboard, the official one, the one that you get by the CNCF. And in this case, we have the search pane showing the results for a query, the DevBcn, right? And we get any resource that matches this name. So the deployments, the pods, replica sets. OK, sounds good. It's OK. It works. However, if we check the network inspector, we'll see that what the dashboard is actually doing is checking the backend, polling the backend every 2 or 3 seconds to get the latest status of these resources. And it will do these requests for each resource it's actually observing. So this is like a very imperative approach, right? Now we have this yet another Kubernetes dashboard. This is the similar page, right? The search pane. Here I'm introducing a query, DevBcn, and it's showing any resource that matches this name. OK, same features, right? However, if we check the network inspector, what we'll see is instead of multiple polling connections, we have a single connection to the backend that was started as soon as the application was loaded. And through this connection, we are actually going to receive the events as soon as the Kube API streams them. So as soon as things happen, we are going to get this immediate feedback. We are responsive. If this wasn't clear, well, let's see it in a diagram. And let's see what the problems are. So this is the official Kubernetes dashboard approach, right? We have, for each of the resources that we observe, maybe 20, we have the front end, which is built in Angular, polling the backend, which is built in Go, every few seconds. The backend propagates these calls to the upstream Kubernetes API in the same fashion. So it's imperative. We don't get the immediate feedback. What are the problems with this? Well, maybe we are going to miss some events. Maybe things are not happening in those 2 seconds or 3 seconds that we are going to miss. The second thing is that maybe you don't know it, but in most browsers, the number of concurrent connections that you can make to the backend is 6. So eventually, if you are polling the backend and making 20 requests, they will go in batches of 6. If some of these connections take longer than expected, eventually, everything might get clogged, and your application might become completely unresponsive or unusable. So this doesn't scale really well, right? Let's now see how this problem is solved with yet another Kubernetes dashboard, how things are happening here. In this case, from the front end, what we are going to do is we are going to open this server-sent event connection to the backend, where every change gets streamed back from the front end as soon as it happens or as soon as the Kubernetes API reports it. From the backend, we are actually going to open individual WebSocket connections, around 30, because we are observing 30 resources, to the Kubernetes API. And the magic happens in the middle, where we are actually going to merge each of these events that we receive from the Kubernetes API into this single server-sent event pipeline. OK, so now let's focus on this backend side that I guess is the most interesting for the purpose of today's talk. So building a resilient and reactive backend with Quarkus. The first thing is, I just want to clarify why I chose Quarkus. Obviously, I might be biased. But yeah, there are also objective reasons. The first one, yeah, we are going to, this is a Kubernetes dashboard. It's most likely going to be deployed into a Kubernetes cluster. So let's use something that's optimized for Java and Kubernetes. Quarkus is. The next thing is that probably we will be providing several replicas of the application components or something like that. So Quarkus provides these fast boot times and low memory footprints because it moves many of the things that happen at runtime, it moves them to build time. And I'm sure that if you've heard about Quarkus, you've already heard about this. If not, tomorrow my colleague Maria has a talk at noon, and I'm sure that you will get more insights about this stuff. The third one, and the most important one for me, is that Quarkus is based on this developer joy. Most of the features in Quarkus are meant to make you as a developer happy. The developer experience shouldn't be a pain. It should be something that, I don't know, it fulfills you, right? It gives you endorphins. So there are many, many features in Quarkus that will help you do this. The Dev UI console, the live hot reloading, live tests, dev services. There are many, many features that provide this developer joy. Next one. So Quarkus provides reactive programming out of the box. Just by adding this Quarkus, now it's Quarkus REST. Before it was Quarkus REST is reactive. It has changed names. But if you add this artifact, you will immediately get this non-blocking I/O provided by Vertex and Neri. You also have this unification of the imperative and reactive world. So you can actually combine both paradigms in the same application just by setting some annotations on your methods. And then, since I was going to implement this server-sent event pipeline, it's really easy to implement this with this dependency. And last but not least, Quarkus has a great integration with the Fabricate Kubernetes client. Again, I might be biased here, but the Fabricate Kubernetes client, for me, is the best client you can have for Java. And with its integration, you can actually get compiled to native your applications without providing any sort of additional configuration. So yeah, that's really cool. OK, so we were at this part where in the backend, we are opening these WebSocket connections to the Kubernetes API, many connections. Then in the middle here, in the backend, it's happening something where we are actually merging those, and we are streaming them through a server-sent event pipeline into the front end. So let's focus on this initial part first, OK? And yeah, this is a very simplified thing that you will find in the yet another Kubernetes dashboard source code, but I think it helps to see, and you can even start from this code if you want. So the first thing is that if you want to implement a server-sent event endpoint, you need to annotate it with these two annotations. Before there were more, but now with this is enough. So get is the standard Jakarta get annotation. And then we have this REST stream element type, which basically tells Quarkus that this is going to be a server-sent event endpoint, and that each of the individual items in the pipeline should be serialized to JSON. Next one is the method signature. So here we are going to use this multi. This is one of the two Mutiny reactive types. In Mutiny, multi is 0 or more items. So basically, again, this is going to tell Quarkus that you're going to stream these items. This part here, we are going to create this multi-emitter. OK? Multi, again, it's part of the Mutiny framework. Usually, maybe if you are using Apache Kafka or some other sort of reactive data source, you won't create the multi yourself. You are actually going to consume that from the upstream integration, or even with PostgreSQL reactive, it's the same. So, but in this case, I'm going to implement this self-healing watchable emitter that we are going to see next. So this is how I'm going to create this emitter. The next thing is that Mutiny provides these callbacks. So for example, if we want something to happen whenever the server-sent event emitter gets subscribed to, we can use this on subscription and invoke, and then whatever is in the Lambda will get called. In this case, this is sort of important because this self-healing watchable emitter is supposed or is designed to run forever. So here, what we are going to tell it is that in case the user navigates away from the website, or I don't know, it closes the browser or whatever, whenever this response is closed, I want to close the upstream subscription. We will see this next. Next one, on failure, if the downstream subscription fails, I'm going to log this warning. And whenever the subscription completes, which should never happen, unless I stop the Quarkus application, I'm going to log this, this debug message. OK, so we saw how we are going to stream these events to the front end. Let's now focus on this middle part, right? How are we going to merge these multiple WebSocket connections into this single server-sent event stream, and also make it resilient, OK? So in the bottom here, I have the diagram that we saw before, and I'm going to highlight some parts as I'm highlighting the code. So you will see which parts are related with the code that we are seeing right now. So the first thing is this self-healing watchable emitter implements a consumer. This is what that multi-create from method we saw earlier expects. And this is that implementation, OK? That's easy. Now, for each of those 30 resources, what I'm telling here is that in an asynchronous way, I'm scheduling this in an executor service, subscribe. subscribe to that WebSocket. We will see the content of that subscribe method next. Here, what I'm actually is binding or creating this callback for the on termination. So whenever the downstream server sent event terminates, what we saw before with the response on close, I want to run the code that's inside here. What's inside here? OK, I want that any active watchers get closed. So this will gracefully shut down anything that's actively being observed. This is that subscribe method that we were talking before. So this is going to actually be called for each of those watched resources, right? Since this is asynchronous, the first thing that we are going to check is if this downstream emitter has been closed. If it hasn't closed, we will continue. This is where we are going to actually start this watcher. So for example, we are taking pods, right? The first line is pods, the second one is deployments, and the third might be services, whatever. So for each kind of resource that we are going to observe, we are going to run this. In this case, it's for pods. So we are opening this subscription. Now we are embracing this failure, right? What happens if this subscription gets closed because the Kubernetes API dies, because there's a network issue, I don't know, whatever? OK, let's log a debug statement. Let's emit a message downstream so that the front end acknowledges that there's some problem with this watcher. Then the front end can act accordingly. And finally, let's reschedule this subscription to the pods watcher. So basically, what happens is that in the event that any of these 30 WebSocket subscription fails, it will automatically try to heal itself, resiliency. What we are doing here, this is the magic part where all of those observed resources get merged downstream into the server sent emitter. So basically, whatever we receive, it's a pod, a deployment, service, whatever, we are going to emit it downstream through the server sent event pipeline. OK? OK, and finally, let's look at the final site, which is where we are actually going to subscribe to these WebSockets by using the Fabricate Kubernetes client. OK? So yeah, again, this is a simplified version of what you find on the Yet Another Kubernetes dashboard project, but I think it highlights quite well what we're doing. So the first thing is that for each of those resources, we are going to run this Kubernetes client, pods, in any namespace, watch. That's how you watch resources using the Fabricate Kubernetes client. It's the same for pods, for deployments, for services, for whatever. But for each of those watch resources, you will need to open this watch connection. The next part here is also adding some resiliency. What we are going to do here is say, hey, this watcher needs to time out after a few minutes. Because maybe you don't know this, but the Kubernetes API is not that reliable. And eventually, some of these subscriptions stop receiving events. So what we are going to do here, since we have this self-healing behavior, is, OK, let's time out every watcher after a few minutes, maybe 10 minutes or 9 minutes, whatever, and let the system self-heal itself. So this is adding this extra layer of resiliency. We're always going to be receiving events. And this is what we saw before, right? That self-healing behavior and that part where wherever we are receiving any event, regardless of the origin, we are going to merge it down the server-sent event pipeline. OK, so yeah, we've seen the backend side. Yeah, I know this is the Java track, but I think that it makes sense that we actually see how these events that we are streaming through Quarkus can be consumed from the front end. OK, so let's see now how we are actually going to open this server-sent event connection from the React application and persist all of the resources that we are going to receive into this internal Redux store. OK, so the first thing that I want to highlight here is that in the front-end application, we are going to persist some sort of snapshot of what we have in the Kubernetes cluster. Everything that we receive in that pipeline will get persisted. And this is going to allow us to have the application work even if it becomes offline. Because in the end, if we check what we have in the Redux state, we have this snapshot of the cluster. Everything that's in the cluster will be in our front end. You will see this in action next. I promise this is the only JavaScript code you are going to see today. I know many people here might hate this, but yeah, just let me show this. So to open this server-sent event connection, we are going to use this event source class that's available in most browsers. So you don't need to add any sort of dependency. Whenever this subscription is open, the first thing that we are going to do is clear any errors that might have been stored in the store, because this might have been a self-recovery. And then we are going to clear the store. Any resources that are in the store are going to be removed, so we get this clean slate. For each message that we receive from the server-sent event pipeline, we are actually going to parse it using this JSON parser and convert it into a JavaScript object, and then persist it into this Redux store. And finally, if there's any error, we'll store this error in the persistence management. And yeah, it's not shown here, but what we are actually going to try and do is to reestablish the connection. Okay? So yeah, what are the advantages of this reactive approach, right? I've talked a lot, but I think that it's better to see this in action. So here on the right, I have the official Kubernetes dashboard. Here on the left, I have the Jacked dashboard. So let's say I query, like before, this DevBcn resources, right? I get this list. Let me do the same here, right? So if I type, as soon as I type stuff, you see that the search is immediately responsive, because I have everything I need in my front-end side. So yeah, let me search for the same term, DevBcn. OK. At this point, they are showing the same. So it should be fine. But what happens if I scale up this application, this DevBcn 2024 deployment? Let's provide 10 replicas. Pay attention to what happens on the left and on the right. You notice that on the left, we are getting changes as soon as they happen. On the right, things took a while longer, right? So the left side is much more responsive. Let's scale it down. So for the user, I think that this is a much, much better experience. And this is clear here. Let's now talk about resilience. Let's stop the official Kubernetes dashboard. So with this statement, I'm going to stop the deployment of the official Kubernetes dashboard. OK, I've stopped it now. Let me try to, yeah. So this application stopped working, right? I mean, this is expected. It's stopped. If I restart it, OK, it reestablishes. I mean, OK. Eventually, it started to work again. Let me do the same with this Jacked application. So I'm scaling it down. Have you noticed that immediately I get this icon where it says, OK, I'm informing the user, the application might not be working as you expected, but still, I can keep, I don't know, navigating. I can still search for stuff. I could even maybe, I don't know, I could even open the editor, even download the resource. So most of the functionality, regardless of the system having failed, is still working. This is one of those advantages that we saw before, right, when we were checking the reactive applications. Of course, there are some things that are not going to work. I cannot stream the logs because I don't have connection to the backend. But still, I mean, the application remains usable. I cannot exec anything in that pod. But yeah, the application still works somehow. If I scale it up, eventually it should self-recover. hopefully. So we should see that this icon is gone. And yeah, now if I want to check the logs, well, it's working. Everything is working. OK? Yeah, so I think that it's pretty clear that the reactive approach is much better from a user's perspective than the imperative approach. However, this is not free. It comes with a certain amount of trade-offs and challenges. First one. So yeah, it's a much more complex system. It takes this complexity in design. You need to plan carefully. You need to embrace this failure. You need to take that into your design phase. So the development time is much longer. Debugging and monitoring. This usually are distributed system. We have this asynchronous communication, so everything gets harder. You need to use specialized tools. However, if you choose wisely the technologies, Quarkus or React, they all have tools or developer tools that will help you to mitigate this challenge. And finally, the learning curve. Obviously, this is a new paradigm for many people, so it takes time to adapt. It takes time to train. However, again, if you choose wisely your technologies, this might not be that big a problem. For example, in Quarkus, you have this mixture of blocking and not blocking code that you can mix and match. So yeah, adapting doesn't take that much, and this isn't that hurtful. OK, and I think that with this, if there's time, we can have some questions and answers. So questions? Yeah.
Thank you. My question is not really regarding this case of using the servers and events for sending the data to the front end, but I think that this technology could be used also for other use cases. And my question was regarding if there were like many events being sent to the front end, could it be any possibility in which we could have any kind of lag on the front end application of not being synced or being able to display this information in real time? And in this case, is there any other alternatives for this?
Yeah, so this is a very good question because it's actually a problem, right? Yeah. Especially with the design of this dashboard. If I deploy this dashboard in an OpenShift cluster, for example, which has millions of resources, then the application might become unresponsive because that Redux state that we saw before becomes full, and this sometimes it's part of it loads into memory. So yeah, I guess that you will need to deal with that in a separate basis. Maybe you want to observe certain kind of resources. You want to limit that number of resources that you want to batch, or maybe you want to use some other kind of persistent storage for your front end or the application that you're designing, or whatever. I think that it's a case-per-case basis. There's no silver bullet. But yeah, I guess this is one of the other challenges, right? If in this example where I was persisting everything to the front end.
Yeah, sure. In this case also, the events that are even emitted, probably there are not too much. So that's it depends for the use case, of course. Yeah. Thank you so much, Marc.
Yeah, thank you. Any other question? OK. So please provide feedback. I think Jonathan said it in the beginning. It's really important for us. If you like the talk or if you don't like it, please say why. I think that's really valuable information for us. And thank you all for attending my talk.